Every Kubernetes operator eventually runs into the sidecar problem. You deploy a helper container alongside your main application to handle logs, proxies, or security. But instead of helping, it causes deployments to fail, destroys data during scale-downs, and eats up cluster resources. To understand why, we have to look at the pod lifecycle. Look at this map. Think of your Kubernetes cluster as a campus, and a pod as a locked room. The kubelet acts as the superintendent guarding the gate. Waiting outside are two containers, the main application, our hero, and the sidecar, acting as the helper. Our mystery is why this helper constantly ends up taking down the hero. To solve this, we need to slow down the clock and watch exactly how the old deployment model fails in real time. Here on the campus map, the superintendent opens the room and pushes both the hero and the helper inside at the exact same moment. But the helper is complex. It takes time to boot up, leaving it unavailable while it initializes. Meanwhile, the fast-booting main application immediately tries to make an external network call. It routes through the sidecar, but the sidecar isn't ready. The connection is refused, and the main app crashes, triggering a CrashLoopBackOff. Let's reset to a healthy running state and look at the shutdown phase. When a deployment scales down, the superintendent sends a termination signal to every container in the room simultaneously. The sidecar receives the signal and shuts down instantly. The main application is still trying to flush its final logs or complete a transaction. It pushes that data out, but the network pathway is already gone. That data is permanently lost. Finally, we have batch workloads. The main application successfully finishes its task and cleanly exits the room. But the sidecar is designed to run forever. It stays active, tricking the cluster into keeping the overall pod status marked as running indefinitely. Crash loops, data loss, and zombie jobs, they all stem from a single root cause. The superintendent has no control over the order of operations. How do we force a strict sequence for startup and shutdown without rewriting our application code? The answer arrived in Kubernetes version 1.28 with the introduction of native sidecars. Here is the first mechanical change to our YAML. Instead of the standard containers array, we move the sidecar into the initContainers block. Then we apply a second contradictory rule. We explicitly tell that initContainer to always restart. Normally, initContainers run to completion and exit, but when the superintendent sees an initContainer explicitly instructed to always restart, it triggers a completely new set of lifecycle rules, officially recognizing it as a native sidecar. Let's replay the deployment with these new rules. Because the sidecar is now flagged as an init container, the superintendent guarantees it goes first. The main application is actively blocked from even entering the room. The entire sequence halts right here. The superintendent waits until the sidecar's startup probe explicitly returns a success signal. Only then does the barrier drop. Both are now running safely. During shutdown, the rules reverse. The superintendent sends the termination signal to the main application first. The sidecar is intentionally kept alive, acting as a stable proxy so the main app can safely flush its final data. Only after the hero exits does the superintendent terminate the helper. But what about batch jobs? If we explicitly tagged the sidecar with a restart policy of always, shouldn't it run forever and trap the pod again? This is where the superintendent makes a final pivot. Once all primary applications successfully complete their tasks, the superintendent actively overrides that restart policy. It forces a clean termination of the sidecar, allowing the pod to natively shift to a completed status. These new rules solve the lifecycle dilemma, but deploying native sidecars in production introduces one critical operational detail. Look at how resources are calculated now. Standard init containers run sequentially, so the scheduler only accounts for the largest one. But because native sidecars run concurrently with the main application, their CPU and memory requests are added together. You must provision node capacity for both. By simply nesting the sidecar under initContainers and setting the restart policy to always, we grant the superintendent total authority over the pod. We replace concurrent chaos with guaranteed sequential startup, reverse termination, and clean job completion.